today we are talking about something near and dear to my heart and something that I hope is extremely useful for all of you, which is how to interpret the results of an OLS regression and how to think about the limitations of our OLS analysis. All right. If you've been here for the whole journey, amazing. If you haven't, don't worry about our roots, but we have previous videos early on in this course where we talked about, hey, what is it that makes some countries wealthier than others? And we're going to talk about wealth in terms of GDP per capita. This is an image from a really great website called Our World in Data. As we can see, GDP per capita is here on the y-axis. Not the only way to measure wealth, but certainly one widely used one. On our x-axis, we have something called the political regime score. This is from a data set called the Polity 4 data set. There's now a Polity 5 out, so hold on to your horses. It's a measure of political regime score. So a score of 10, according to this measure, is a fully democratic country, and a score of -10 is a not at all democratic or fully authoritarian or autocratic country. So let's explore the relationship between democracy, our polity score, and GDP per capita. Does being a democracy make a country more wealthy? We're not at all going to be able to say anything truly about causality, but we could think about making some predictions. So my theory that I'm working with is that regime type affects GDP. My DV, my dependent variable in this case, is GDP per capita. That's what I'm predicting. My IV is the polity score that a country has, and it can range from -10 to 10. I have a hypothesis. My hypothesis, H1, there is an effect of polity score on GDP. In other words, I am predicting that my coefficient, my regression coefficient, is not equal to 0. Note, I could make a hypothesis that was directional. I could say hypothesis 1, there is a positive effect of polity score, or there is a negative effect of polity score. And our interpretations might be slightly different, but it's roughly the same idea. I'm just setting it this way to keep it simple. My null hypothesis is that there is no relationship between polity score and GDP. My null hypothesis is the boring world. It's the world of no relationship. So therefore, I'm predicting that my coefficient in my linear regression output is going to be 0. We'll break that down specifically when we look at the results table. Now, note, our dependent variable is continuous. What I mean by continuous is that in principle, our dependent variable could take on any value. We're certainly rounding in this graph. We've 20,000, 40,000, 60,000 GDP per capita. But in principle, a country could have a GDP per capita that is 60,201, 60,202.68, 200,487.99999. I'm just going to say numbers for another half hour. It could take on any value. The polity score is what we call discrete. It's not continuous because it can take on values that are whole numbers, -10, -9, -8. But what we care about in this case is that our DV is continuous. That needs to be the case for our linear regression to make sense. Just by looking at this, not even that hard, we can have some issues about the linearity of this relationship. A linear regression does require linearity between its variables. I am going to proceed nonetheless because I think it's very important to show you that you can still do a linear regression on non-linear relationships, but you need to be aware of the fact that just because your results come out without an error, say in Python, doesn't mean that your results are actually useful. So I purposely use this example because I want to highlight how easy it is to make terrible mistakes. All right. So this is not going to stop us from actually carrying out the regression. Our computer doesn't care that it's nonlinear, but we as researchers need to do a lot of thinking both before the analysis, during, and after. Is this the right model? First, always evaluate the data. We want to say, hey, how are we measuring democracy? Are we conceptualizing right? Are we operationalizing right? Are there errors in the data? Again, go back to the earlier lectures on evaluating data. We get all our information from the code book. We should absolutely familiarize ourselves with the data. Are we missing lots of pieces of data? What's in it? Get our heads around it. Suppose I've got my data in my Jupyter notebook and I'm taking a look. So this is what the data looks like. We have entity. So each country, or in some cases, territories or entities if they're not full countries. There's a code for them. Great. GDP, note we have a lot of missing variables, especially for older years. And polity score, again, a lot of missing variables, especially for older years. And we have population. We're not really going to do much with that at the moment. We can find the correlation between all of our numeric variables by simply writing data.core. I've just named my data set data. And so we can inspect the correlation right here. And we see, okay, the Pearson's correlation coefficient, assuming a linear relationship, is almost 0.2. So pretty weak, but positive correlation. All right, here's our scatter plot. As you can see, our x variable, which I've now mapped to the y just to keep us on our toes, is discrete. It takes on specific values, whereas indeed our dependent variable is continuous. So definitely not a linear relationship, but we persist nonetheless because we can. All right. So let's talk about how we're going to actually interpret the coefficients. You can run a linear regression in Python in 2 lines of code. There's a few more lines of code to import packages and data, but the actual thing itself is just right here. The way I've written it shows GDP tilde polity. GDP is our dependent variable. The code is all described in great detail in the online textbook. We're going to keep it conceptual in this video. All right. So a few things to interpret. We're not going to cover all of these. In future statistics courses, you will eventually get to all of these. So the intercept is 9,816.7403. The first thing I want to flag is that linear regression and many statistical analyses will offer a very, very, very specific number, which many people incorrectly interpret as exact and correct. You can be as specific as you want, but if our model is not appropriate for our data, this level of specificity doesn't matter. So I really urge you, we keep these decimals in as though we're really making some point prediction, but in reality, we're working with data that's not even linear. And so, in a limited set of variables. So I wouldn't, people tend to get dazzled by lots of decimal points. We're estimating here. All right. So the intercept is 9,800. The coefficient on polity, our independent variable, is 411.1332. Okay. What does that mean? So here's what this means. If you're preparing some homework for a statistics course, this is how you say it. When the polity score is 0, GDP per capita in the countries, in the entities in our data set is $9,800. Okay. More specifically, output side, real GDP per capita in 2011 international. Okay. All right. The coefficient, a 1 unit increase in the polity score is associated with a $411 increase in GDP per capita. In other words, when the polity score is 0 for any country, this is our prediction, for any country with a polity score of 0, neither autocratic nor democratic, when a country has that score, we can anticipate that GDP per capita will be just under $10,000. Our coefficient says if we go up by 1, so if I'm at 0 and I say, yikes, I want more money, will increasing my level of democracy do much for my GDP per capita? Well, our model is predicting that a 1 unit increase in our polity score, going from a polity score of 0 to 1, will increase our GDP per capita by $411. Now, because it's nonlinear, we know this is not that helpful. It could be the case that as we have a higher polity score or a lower polity score, that effect will be different in real life. But just to get the words in our brains, we're going to keep going. Again, just because you can do it doesn't mean you should. Regression is so powerful and it is so widely misused. I truly am using a bad example on purpose. I'll post a good example. Remind me. So, okay. So what have we learned? Well, we have questions. So is $400 a lot of money? Is it worth, if I want to increase GDP per capita by 400, I mean, it is a lot of money, but is it at the level that a government would care? Statistical significance. Oh, I've been really avoiding this term for a long time in this series because I have some problems with the term statistical significance, but we might want to know, is it statistically significant? More on that in just a moment. Is there substantive significance? Meaning, is 400 a lot? Is it hard to change polity score by that much? That kind of gets back to do we care about these results? Is polity a good predictor of GDP overall? Well, from the coefficient alone, we can't really say. What about this nonlinearity? Yeah, big problem. Endogeneity, confounders, there's all kinds of things we need to be thinking about. Is our data just total garbage? So again, I don't know if I can make this point too many times. I can. You don't need to tell me I'm doing it. There's so much more to learning from our data than just putting the data in our program and generating results. All of this thinking, all of this evaluating, at every stage of the data science process is where we're actually going to make discoveries and decide what we can learn and what we cannot learn from this data. Generating the results is, dare I say, the easiest part. Oh God, cancel me, just cancel me. Let's push on. The next thing I want to focus on in our output table is p-values. So p-values, we can look at our regression results right down here. We see that in our regression of polity on GDP, we see a p-value is 0.00. This means, here's how we interpret our p-values. The probability of seeing a coefficient of $400 if the null hypothesis is true is 0. If we expanded this out, it's probably 0.0004321. There's probably numbers at the end of it. It's probably not exactly 0. If the null hypothesis is true, the probability of seeing the coefficient that we got in our analysis is 0. And remember that our null hypothesis is that there's no relationship. So we consider this result statistically significant. Statistical significance is something that is generally thought of as occurring when we have a p-value of less than 0.05 or less than 0.01. Those numbers are basically historical accidents. They're matters of convention. There's nothing magical about those numbers. That's one of the reasons I don't really say those numbers. It's up to us to say, what's the probability of seeing this coefficient if my null is true, and decide what probability we're comfortable with. Are we comfortable with a 10% probability, a 5% probability, and so on? We're at 0.000 something, so we don't really have to worry about the threshold yet, but we can conclude, indeed, that this result is statistically significant, the 0.01 level, 0.001 level, and so on. Now, as stated, when the p-value is dead on 0, as it appears to be in this table, it's certainly clearer. But what if the p-value were 0.01, 0.05, 0.1, 0.5? There's a 50% chance that if the null hypothesis is true in the world, we would get this result. Does that make us feel good? Nah. So at what point do we say something is not significant? Arbitrary, up to us, matter of convention, and so on. It doesn't tell us much about substantive significance. So even if every time we ran our study, we would see a coefficient roughly around 400, that doesn't mean that 400 is worth writing home about. On to confidence intervals. Confidence intervals are widely misunderstood. Have you noticed a theme for all of these? So if we conduct our study many times, 95% of the time, the confidence intervals we generate will capture the true coefficient. Now, it's 95% because this is a 95% confidence interval. We could do 90%. We could say 99%. 95 is the default in this particular stats models program in Python, and it's pretty standard as far as starting points for linear regression goes. So this is very important to say it the way that I've just said it. We'll keep revisiting this point. It's misunderstood a lot. So, okay, the bigger the sample, the narrower our confidence interval. If the confidence interval contains 0, we do not have statistically significant coefficient. If for some reason we are forbidden from looking at the p-values, we can look at the confidence interval and say, gosh, does it contain 0? If it contains 0, then that means there's a pretty decent chance the true coefficient out there in the world is actually 0, meaning the null hypothesis is something we can fail to reject. The confidence interval represents the range for the coefficient. So 4.11 is our predicted coefficient. The 95% confidence interval is between 365 and 456. The reason I belabor how we talk about confidence intervals is that it is incorrect to say that we are 95% confident our coefficient is in this range. That is how way too many people say it. That is incorrect. Let me restate the correct version again. If we run our study many times, 95% of the confidence intervals we generate will contain the true value for the coefficient. That's a clunkier way to say it, I know, but it's the accurate way to say it. And this distinction is super important. So a confidence interval that we generate either contains the true value or it doesn't. There's no probability that it's in there. If I generate 100 confidence intervals, 95 of them will, yes, contain the true value, and 5% of them will not. So no probability, there either is or there isn't. So in other words, to say the whole thing again, 95% of the confidence intervals we generate will contain the true coefficient. This is a lot. So these are the 3 that I really focus on with my students in my intro data science course. I want to jump up to the last little piece that we'll focus on for our purposes right now. So let's talk about the R squared. R squared is the percentage of the variation in Y that is explained by our entire model. When there is just one independent variable, such as here, which is the polity score, the capital R squared equals lowercase r squared, which if you watched 2 videos ago, the video on correlation, is the correlation coefficient. The correlation coefficient squared, the Pearson's correlation coefficient squared, is our capital R squared. Awesome, amazing. I just like it when the world comes together. What does this mean? How do we interpret our capital R squared? Our model explains 3.8% of the variation in our dependent variable. So our dependent variable of GDP per capita we say, hey, I want to predict GDP per capita. Well, if we know the polity score of a country, that's going to predict 3.8% of the variation in our DV. Is this a lot? Feels like a low number. Is it a low number? Well, different fields have different threshold for what counts as a good R squared. In the social sciences, it's very common to have R squareds less than 50%. If you're working in fields that are a bit more predictable, or that we have a better handle on the various pieces and how they drive things, or just fewer pieces are needed to understand a particular phenomenon, you might be looking for R squareds of 90%. As a social scientist, I've never seen such a thing in my life. But even as a social scientist, I would say that 3.8 is small. So my students often ask at this point, well, what's the official threshold? What's the cutoff? Which is part of why I don't say the 0.05 very much for p-values, because we tend to focus on it and say, like, oh, that's the cutoff. There's no magic number. There's no magic number for the p-value. There's no magic number for the R squared. It's up to us. How much do I want to explain? Do I think this is enough to keep going if I want to predict or understand? It's a clue to me that we're not really explaining variation in GDP. If we have more than one R squared, we're going to use the adjusted R squared. Basically, what happens there is it adjusts for adding variables. Just adding variables is just going to push up our R squared. Adjusted R squared penalizes you for adding more variables. It's calculated in a different way. I'm not going to get into that here, but I want to flag that. So let's just look quickly at a multiple regression. I'm going to use the variable population because it's literally the only variable that we haven't used in the data set that I have. And it's just truly for illustrative purposes. And again, it's easy to generate, not necessarily informative, but easy to generate. So here are our results. So now we have a coefficient for our polity score, but we also have a coefficient for the population. A 1 unit increase in polity is associated now with a 412 unit increase in GDP per capita. I think we were at 413 before. But the big difference is this is holding population constant. That's how we interpret our coefficient when we have more than one variable, holding these other variables constant. Our p-values are hanging out at 0 for polity. For the population, we now actually see a number. That's nice. Our confidence interval does not contain 0 for our coefficients. For either coefficients, it's quite small for population, but it's not 0. And it is significant at the p is less than 0.01 level. Let's look at population more specifically. Okay, ready? A 1 unit increase in population, so one more person added to the population of a country, is associated with a, let's go, 0.00004755 decrease in GDP per capita holding polity constant. If I want to trash the GDP per capita of a country, adding one person is not going to get me very far. So that's our substantive significance is tiny, but our statistical significance is very strong. That's the difference. Oh, it's so important. All right. So it's significant. Confidence interval doesn't contain 0. It's low, but it doesn't contain 0. And our R squared. So our R squared, we're going to look at the adjusted R squared because we've got more than one independent variable, 0.039. We are explaining now almost 4%. We are explaining 3.9% of the variation in Y. Not so great. So did this model improve anything? Did adding another variable improve anything in general? Is this model any good? So no, not really. I would say we didn't get much more explanatory power. Certainly adding population didn't help us do much more prediction. Population has a tiny effect. It's statistically significant. It's miserably tiny. We could certainly multiply it. Adding one person is not so meaningful. We could say, what if we increase population by 10,000 or 100,000? That would push up the numbers a bit, but I still don't feel like that's like where I would go if I'm trying to increase the GDP. And remember, we like parsimony. We prefer a theory of equal or roughly equal explanatory power. So if I had to choose between the two, the one with 2 variables, 2 IVs, and 1, I would stick with the 1. And hey, here we go. We're going to be discussing finally what we've been running from, which is the fact that we're violating a lot of assumptions in OLS. Again, I cannot overstate this. Running a regression in a program and having that regression work, like you don't get errors, you get numbers, you can sit around and interpret the numbers just like I have, doesn't mean we're learning anything, doesn't mean it's the right analysis, and it doesn't mean that that it's useful even a little bit. All right, so it does seem cool though, right? I love the fact that we can make these kind of point predictions. We can talk about different aspects of how two variables go together. It is very valuable. It's certainly an improvement over just a correlation coefficient or looking, but, and I'm not the only one to use this analogy, but there are a lot of limits to OLS. So in other words, it's super powerful, but with great power comes great responsibility. So OLS is so common. So many people use OLS. It works with more than one independent variable. You can do all kinds of interesting things, but in order to generate reliable results, you need to make several assumptions. If these assumptions are violated, our results may be unreliable. So OLS and regression generally is misused because it's so simple and so easy to do once you kind of get the code and have a sense of how to interpret it. You just generate regressions until the end of time, but it has so many assumptions that most people ignore. So we need a reasonable sample size. OLS really doesn't work if we have like 4 observations. 30 is kind of a rule of thumb. For the most part in data science, we're working with data sets that are much larger than that. So it's kind of less of an issue. But generally speaking, we do need to make sure that we've got a reasonably large sample size. The smaller the sample, the less significant our results are. One of the other reasons I am very skeptical of statistical significance as kind of the thing that we hang our hat on when deciding if an analysis was any good is that if you have a huge sample, you're much more likely to get statistical significance just based on the sample size alone. We're assuming a linear relationship, and this is so often overlooked, and we're assuming effectively that a line is a best fit. If it is not, the coefficients mean very little. I think our coefficients in the example we've done in this video mean very little because, as you remember, the relationship was nonlinear. Let me see if I can do it. And kind of like a flat U. So I would do a nonlinear regression. We're not going to cover that in this course, but that's what I would do. We want to make sure we have minimal outliers. This is a broader conversation, but just to flag it here, extreme values can really affect OLS, especially because we're squaring the residuals in order to find our best fit line. It's very sensitive to outliers. Students at this point always ask, what counts as an outlier? How far away does one value have to be for us to call it an outlier? And there's no hard and fast rule. Notice a theme here. There's no hard and fast rule. It's kind of up to our subject matter expertise. Typically, what I recommend is do an analysis with the outliers, do it without, and talk about whether or not it's robust to outliers. And then talk about if it's not robust to outliers, meaning removing the outliers that I've decided are outliers based on my knowledge of the thing that I'm studying. If removing outliers changes the results substantially, have a conversation about why that is and whether or not removing those is helpful. We're not trying to make a tidy picture for the sake of it. We're trying to best reflect what's going on in the world. So to make this a little bit more concrete, if we tried to do something related to the income of Americans or the wealth of Americans, there are a number of outliers like Elon Musk, Jeff Bezos, and others who have way more money than most of us. And if we tried to do some kind of prediction on predicting wealth of Americans, we would be quite off if we included them and tried to make claims about most Americans. So if we want to predict the overall income of people in the country, we'd include everything. But if we want to say, like, what are most people going to, how are most people going to be affected in terms of their income, it might make sense to remove those outliers. So it's much more about what are we trying to explain? Does it theoretically make sense to remove that outlier? If so, do so. The temptation can be to just remove them to get a kind of nicer looking set of results. Don't do that. And if we have these extreme values, basically coefficients mean a lot less. These are a little bit trickier. I will go probably frustratingly quickly over them, but I do want to flag them. So we want little or no multicollinearity. We want it to be the case that the IVs cannot predict one another. For example, if I'm predicting the wealth of countries and my independent variables are they have elections, they have freedom of speech, they have freedom of assembly, and an independent press, all of those variables kind of predict each other because they're all components of most democratic countries. So we would be violating our assumption of little or no multicollinearity. And the result is our coefficients are going to be less precise. Remember how I said we could get decimals down to like 0.07777 is my coefficient? Yeah, but the whole thing could be wrong. Homoscedasticity is that the variance of the residuals is the same. This means we're just as good at predicting our dependent variable for low values of X as we are for high values of X. We want homoscedasticity. If the variance is not the same, we are in a world of heteroscedasticity, and this can really affect the significance in our results. We want to make sure that we don't have autocorrelation. This is an issue when we have results over time. So we want to make sure that one value in time doesn't predict its own value later in time. If we do have autocorrelation, this also can affect our significance. And we really want a continuous dependent variable. So what this means is that our variable that we're predicting is not discrete or categorical. And this is because the output is going to be continuous. So in other words, we are going to get a number like 0.076 for our coefficient. And if we're predicting something that's either a 0 or a 1, 0.076 doesn't mean much. We certainly can do types of analyses where we have a discrete or categorical dependent variable, for example, a logistic regression. We will not be covering that in this course. So for OLS, we need a continuous dependent variable. Independent variable, not required. I mean, it's required, but continuousness is not required. All right. This video is so long. Thank you. I'm shocked if you're still here. Great. All right. So OLS is extremely simple to do. If you watched all 3 of these videos, these ones in this series, send me a note. I'll send you a medal. OLS is extremely simple to do. 2 lines of code in the examples that we've done. Other steps in our research, for example, just cleaning the data to get it ready to go, is likely going to be way more time consuming in your work than the actual OLS, even though the OLS is like the big show, right? It's very easy to do. Here's an analogy no one's going to like. I'm just thinking of this now. So if you're doing a circus performance, who hasn't, you're on stage and you're showing off your skills, your costumes, your makeup, and you get 3 minutes to kind of show it all off. But the amount of work that goes into those 3 minutes of like flawless execution and drama and a mood and a choreography and all this stuff and strength to be able to, flexibility, all this is years of training, hours of makeup and warming up before the show, just for this kind of 3 little minutes. That's how you can think of OLS. It's like the big impressive thing, but it's not possible without tons of preparation and work and thoughtfulness. That analogy is for the circus performer data scientists who are watching this. It's too easy to do OLS poorly, incorrectly, or without understanding at all what you're doing. And I'm sorry to say, I see it everywhere. So many assumptions need to be met in order to accurately infer coefficients and significance. It's not often obvious. It's almost never obvious what model to use. Should we have 1 independent variable? Should we have 2? Should we have 3? How are those variables related? We've assumed that they're also just additive, but there are other relationships our independent variables could have. We need theory to guide us. The best practice is to share the results of many models. So for example, if I were to publish my garbage results that we've gone through in this video, I would say, hey, here are the results when I set 1 independent variable. Here are the results with 2 independent variables and all in one big chart. The outputs are so frequently misinterpreted. Now that you've gone through this video, prepare to be irritated a lot when you hear people talk pretty fast and loose about statistical significance, confidence intervals, coefficients, all the rest. And as we said at the beginning of this unit, OLS is truly just the beginning. This is really the backbone of many, many, many types of regression that you can go on to study. We have regressions for non-continuous DVs, like we talked about, for nonlinear relationships, special types of regression specifically for cases where there are outliers that we want to make sure to incorporate thoughtfully in our model, and a ton more. If you're feeling like this is interesting and intriguing and want to keep going, fear not. This is but the first step in a long, wonderful journey. So to close on something depressing, it is a really great and powerful tool, but it's also really dangerous because it can be so frequently misinterpreted. And again, we haven't even talked about all the other matters of research design and errors in the data and all that kind of stuff. So I'm so glad that you have sat through this video. It's a big one. It's super important if you're planning on doing any kind of regression. And I really do encourage you to do it, but be as thoughtful as you possibly can. Be transparent about your work and be transparent about the limitations of your work. And then we'll all really start learning things. All right. So thank you so much. I will see you all in the next video.